Welcome to this episode, where we dive into the fascinating and complex world of distributed systems. Today, we're focusing on two key concepts that are vital for their functionality: reliable communication and consensus. These are the cornerstones that help ensure distributed systems operate smoothly, even when faced with various challenges, such as failures and faults. We'll explore what makes these concepts so essential and the strategies we use to tackle the hurdles that come with them. Let's kick things off by discussing exactly once delivery. This idea is all about ensuring that messages in a distributed system appear to be sent only once, even though in reality, achieving this is tricky. We can't completely guarantee that a message will only be sent a single time, but we can create an illusion of reliability. This is done through careful message processing and the ability to recognize and disregard duplicates. The real challenge arises when we consider the risk of message loss or duplication, especially in asynchronous environments where timing isn't always predictable. To illustrate the complexities of reaching consensus, we can look at the two generals problem. Imagine two generals trying to coordinate an attack, but they have to communicate their plans over an unreliable channel. Messages can be lost or delayed, making it incredibly difficult for them to agree on when to strike. This thought experiment highlights the inherent difficulties in achieving consensus when communication isn't guaranteed, showing us just how vital it is to have robust protocols that can manage uncertainty. Building on that, we encounter the FLP impossibility problem, named after Fisher, Lynch, and Patterson. This problem sheds light on a fundamental limitation within asynchronous systems. If even one process can fail, consensus cannot be achieved within a guaranteed time frame. This realization is crucial for understanding the boundaries of distributed algorithms and why timing assumptions are so important in simplifying the consensus challenge. Now, while the FLP impossibility problem might seem daunting, it also opens the door to a potential solution through timing assumptions. By implementing certain timing guarantees, we can design systems that are more adept at reaching agreements, even amidst the uncertainties of asynchronous communication. These timing assumptions allow us to create algorithms that operate within defined time limits, ultimately enhancing the reliability of consensus. Next, let's explore the different failure models that can impact distributed systems. Understanding these models is essential for crafting resilient systems capable of managing faults effectively. We start with crash faults, which happen when a process unexpectedly stops running. In the crash recovery model, a process can pause and later resume its operations, necessitating a durable state and a recovery protocol to handle interruptions. This capability is crucial for maintaining system integrity when unexpected failures occur. Then we have omission faults, which come into play when processes skip steps or fail to communicate entirely. These faults can stem from network issues, like congestion or partitions, leading to situations where a process seems operational but is out of sync with others. Omission faults can be particularly challenging because they're often hard to detect, yet they can significantly disrupt the consensus process. The most intricate type of failure we'll discuss is Byzantine faults. In this scenario, a process might act incorrectly while still adhering to the algorithm's protocol. This can create misleading communication, making it tough for other processes to reach a consensus. Byzantine fault tolerance is a crucial area of study in distributed systems, as it demands sophisticated strategies to ensure that the system continues to function correctly, even in the presence of erratic or malicious behavior. Throughout our discussion, we've emphasized the importance of understanding these failure models and their implications for system design. By recognizing the different types of faults that can occur, developers can create more robust systems that not only aim for consensus, but also maintain their functionality amidst adversity. This knowledge is vital for building distributed systems that are resilient and capable of navigating the unpredictable nature of real-world environments. As we wrap up this episode, let's take a moment to reflect on the complexities of achieving reliable communication and consensus in distributed systems. From the challenges highlighted by the two generals problem and the FLP impossibility problem to the intricacies of various failure models, it's evident that designing effective distributed systems requires a deep understanding of communication protocols and the potential faults that can arise. By exploring these concepts, we equip ourselves to create systems that are not only efficient but also resilient in the face of challenges. Thank you for joining us today, and we look forward to continuing this exploration of distributed systems in future episodes.